Let's delve into the world of spiral pipe manufacturing, a highly efficient and versatile process for creating strong, durable pipes used in everything from HVAC systems to structural components. Unlike longitudinally welded pipes, spiral pipes are formed by uncoiling a continuous strip of steel and feeding it at an angle into a forming machine. This angle, the helix angle, dictates the pipe's diameter. As the strip is bent into a helix, its edges are continuously welded, creating a spiral seam. Finally, the continuously forming tube is cut to the desired length. This method boasts several advantages: a superior strength-to-weight ratio due to the evenly distributed stress of the spiral weld, remarkable diameter and length flexibility, cost-effectiveness stemming from continuous production and minimal material waste, and a smooth interior surface that reduces friction. The manufacturing process itself can be broken down into distinct stages, each involving specialized machinery. First, the uncoiling and strip preparation phase begins with a robust uncoiler, or decoiler, that holds and unwinds the steel coil. This machine often features a hydraulic or pneumatic expansion mandrel to grip the coil, motorized rotation for controlled unwinding, and a tension control system to prevent slack. A strip leveler may be used to remove any curvature from the steel, ensuring consistent forming. Depending on the chosen welding process, edge preparation might involve an edge milling machine to create a precise bevel or shot blasting/grinding to clean the edges for optimal weld integrity. The heart of the operation is the helical forming stage, performed by the forming mill or spiral pipe mill. This machine utilizes a series of precisely positioned rollers, arranged in a cage-like structure to progressively bend the steel strip into its helical shape. These rollers, categorized as inner and outer forming rollers, are often driven and synchronized, with guide rollers maintaining the correct helix angle. Crucially, an angle adjustment mechanism allows for precise control of the helix angle and thus the final pipe diameter. A powerful drive system pulls the strip through the machine. Immediately following the forming rollers is the welding station. Here, the meeting edges of the strip are continuously joined. The most common welding process for thicker materials is submerged arc welding (SA), where a consumable electrode is buried under a granular flux, creating a protective slag. For thinner materials, gas metal arc welding (GMAW/MIG), which uses a consumable wire electrode shielded by an inert gas, is often employed. High-frequency induction welding (HFIW) is a specialized option for thin-walled pipes, using high-frequency current to create a forge weld. Regardless of the method, a sophisticated welding parameters control system monitors and adjusts current, voltage, travel speed, and other factors. Weld tracking systems, often using optical or laser sensors, are highly recommended to maintain consistent weld quality. The final stage in the continuous process is cutting. A cut-off machine, positioned at the end of the line, severs the pipe to the desired length. Common types include flying shears, which make clean cuts without stopping the forming process, plasma cutters, and saws. The cut-off control system is synchronized with the forming machine and programmed for precise cuts. After cutting, optional post-welding processes might include weld inspection using non-destructive testing methods, like ultrasonic or radiographic testing, beveling of the pipe ends, coating application for corrosion protection, and hydrostatic testing for high-pressure applications. In essence, spiral pipe manufacturing combines precision engineering, advanced welding technology, and sophisticated automation to produce high-quality, versatile pipes for a wide array of industries. U.S. Pipe Fabrication is a leader in the manufacturing of ductile iron pipe and related piping components, serving industries such as water distribution, wastewater management, and industrial piping systems. U.S. Pipe Fabrication, like many in the industry, focuses on creating custom pipe systems for various applications, including industrial, commercial, and infrastructure projects. Their expertise lies in transforming raw materials into precisely engineered piping solutions. The initial stage of pipe fabrication involves meticulous material selection and preparation. This includes receiving raw pipe, fittings, and flanges, which undergo thorough inspection to ensure they meet project specifications. Cutting is a critical step, often performed using automated plasma cutters or saws, depending on the material and required precision. These machines allow for accurate and efficient cutting, minimizing waste and ensuring consistent dimensions. For complex shapes and bevels, CNC, computer numerical control, machines are employed, providing exceptional accuracy. Following cutting, the components move to the fit-up and welding stage. This is where the individual pieces are assembled, according to the engineering drawings. Skilled welders, certified in various welding processes like TIG, tungsten inert gas, MIG, metal inert gas, and SAW, submerged arc welding, join the components. Welding machines are precisely calibrated to ensure strong, leak-proof welds. Automated welding systems are increasingly used for high-volume production and complex geometries, enhancing consistency and efficiency. To ensure weld integrity, non-destructive testing (NDT) methods are employed, including ultrasonic testing, radiographic testing, and magnetic particle inspection. These techniques detect any internal or surface defects, guaranteeing the quality and reliability of the welded joints. After welding, the fabricated pipe spools undergo cleaning and surface preparation. This may involve blasting, grinding, or chemical treatments to remove contaminants and prepare the surface for coating. Coating is crucial for corrosion protection and can involve various methods, such as epoxy coating, powder coating, or galvanizing. Automated coating lines ensure uniform application and consistent thickness. Hydrostatic testing is the final step, where the assembled pipe system is subjected to high pressure to verify its structural integrity and leak tightness. This test ensures that the fabricated piping system can withstand the intended operating conditions. Throughout the process, advanced quality control measures are implemented, including dimensional inspections, material traceability, and documentation. Modern pipe fabrication facilities utilize sophisticated software for design, planning, and production management, enabling precise control and efficient workflow. The use of 3D modeling and building information modeling (BIM) allows for virtual assembly and clash detection, minimizing errors and ensuring seamless installation. ArcelorMittal's Jubail facility is a prime example of modern seamless pipe production, designed to meet the demanding requirements of the oil and gas industry. The process begins with high-quality steel billets, which are heated in a rotary hearth furnace. This furnace ensures uniform heating, crucial for the subsequent piercing operation. The heated billet is then fed into a rotary piercer, where a mandrel is forced through its center, creating a hollow shell. This piercing process relies on heavy-duty rollers and a precisely controlled mandrel to achieve the desired wall thickness and diameter. The rotary piercer's design minimizes stress on the material, ensuring a high-quality initial hollow. Following piercing, the hollow shell undergoes elongation and wall thickness reduction in a plug mill. This mill uses a series of grooved rolls and a plug mandrel to stretch the shell and reduce its wall thickness. The plug mill's precise control over rolling parameters is essential for achieving the final pipe dimensions and mechanical properties. The elongated shell is then reheated and further processed in a stretch-reducing mill. This mill refines the pipe's diameter and wall thickness, providing the final dimensions with exceptional accuracy. The stretch-reducing mill uses a series of closely spaced stands, each with precisely calibrated rolls, to achieve the desired dimensions. After the stretch-reducing mill, the pipe undergoes a series of finishing operations. This includes cooling, straightening, and cutting to the required length. Cooling is controlled to ensure the desired microstructure and mechanical properties. Straightening is performed using multi-roll straighteners, which eliminate any residual curvature. Cutting is done using high-speed saws or plasma cutters, ensuring precise lengths and clean edges. Throughout the process, rigorous quality control measures are implemented. This includes ultrasonic testing, electromagnetic testing, and hydrostatic testing to detect any defects. Ultrasonic testing uses high-frequency sound waves to detect internal flaws, while electromagnetic testing identifies surface and near-surface defects. Hydrostatic testing subjects the pipe to high pressure to verify its strength and leak tightness. These non-destructive testing methods ensure that every pipe meets the stringent quality standards required for oil and gas applications. ArcelorMittal's Jubail plant also incorporates advanced automation and control systems. These systems monitor and control every stage of the process, ensuring consistent quality and efficiency. The use of advanced sensors, actuators, and control algorithms allows for precise control of temperature, pressure, and speed, minimizing variations and maximizing yield. Additionally, the plant utilizes sophisticated data acquisition and analysis systems to track production parameters and identify areas for improvement. This data-driven approach allows for continuous optimization of the manufacturing process, ensuring that ArcelorMittal remains at the forefront of seamless pipe technology. Repco In is a specialized engineering and manufacturing company that focuses on providing complete, turnkey solutions for the production of LPG, liquefied petroleum gas, cylinders. Turnkey means they handle every aspect of setting up a production facility, from initial design and equipment supply to installation, commissioning, and even training. They don't just sell individual machines, they deliver a fully operational production line, ready to start manufacturing cylinders. Their expertise lies in metal forming technologies, particularly for cylindrical components, and they offer solutions tailored to various types of LPG cylinders: domestic, industrial, and picnic, smaller, portable types. Their solutions are structured around three main production lines: blanking and body forming, welding, heat treatment, and hydrostatic testing, and surface coating and finishing. Repco In's manufacturing process is divided into three interconnected lines, each responsible for a specific stage of cylinder production. Blanking and body forming line is where the raw material, typically steel sheets, is transformed into the basic cylindrical shape of the LPG cylinder. This line involves several key processes and machines. Blanking is the initial step, where flat steel sheets are cut into precisely sized circular blanks, discs, using a blanking press. This press uses a powerful die and punch to shear the steel sheet, creating the starting material for the cylinder body and the top/bottom domes. The accuracy of the blank is crucial for the subsequent forming processes. The circular blanks are then deep drawn into cup-shaped components. Deep drawing is a metal forming process, where a blank is radially drawn into a forming die by the mechanical action of a punch. This creates the half shells of the cylinder body and the top and bottom domes. Multiple drawing stages might be necessary, with intermediate annealing steps to prevent cracking and improve the steel's formability. Repco In likely utilizes hydraulic presses for deep drawing, offering precise control over force and speed. After deep drawing, the edges of the formed parts are trimmed to the exact dimensions, and any necessary holes are pierced using specialized trimming and piercing presses or dies. Repco In is known for its expertise in flow forming. This is a highly efficient process for creating seamless cylindrical bodies. In flow forming, a thick-walled preform is rotated at high speed and progressively formed over a mandrel by rollers. The rollers apply localized pressure, thinning the wall and extending the length of the cylinder to its final dimensions. This process significantly improves the material's strength and grain structure. Flow forming machines are highly specialized and require precise control over roller movements and forces. The cylinder heads, or end caps, are frequently formed using a metal spinning process. This entails rotating a metal disc at high speed while pressing it over a spinning die. The metal takes on the shape of the tool. Welding, heat treatment, and hydrostatic testing line focuses on joining the cylinder components, ensuring structural integrity and verifying safety. The two halves of the cylinder body, produced on the body forming line, are joined together using circumferential welding. This is typically done using automated welding processes like submerged arc welding or gas metal arc welding. Repco In would integrate robotic welding systems or specialized circumferential welding machines to ensure consistent, high-quality welds. The welding parameters are precisely controlled to achieve full penetration and minimize defects. Some cylinder designs might require a longitudinal seam weld. This would also be performed using automated welding processes. The foot ring and the valve boss are welded to the cylinder body, typically using GMAW/MIG welding. After welding, the cylinder undergoes heat treatment to relieve stresses introduced during the forming and welding processes. This is crucial for preventing cracking and ensuring long-term durability. The specific heat treatment process depends on the steel grade and cylinder specifications. Repco In would integrate specialized furnaces with precise temperature control and controlled cooling cycles. Hydrostatic testing is a critical safety test where the cylinder is filled with water and pressurized to a level significantly higher than its operating pressure. This test verifies the cylinder's structural integrity and detects any leaks. Repco N provides automated hydrostatic testing systems that control the pressurization, holding time, and depressurization, ensuring compliance with relevant safety standards. The system also monitors for any permanent deformation or leakage. Surface coating and finishing line focuses on protecting the cylinder from corrosion and providing an aesthetically pleasing finish. The cylinder surface is prepared for coating by shot blasting. This process uses abrasive particles propelled at high speed to remove any scale, rust, or contaminants, creating a clean and roughened surface for optimal coating adhesion. Repco N would integrate automated shot blasting machines with dust collection systems. The cylinder is then coated to protect it from corrosion. This can be done using liquid paint or powder coating. Powder coating is a more environmentally friendly option and provides a durable, uniform finish. Repco N would provide automated coating booths with electrostatic spray guns or conventional spray systems, ensuring consistent coating thickness and coverage. After coating, the cylinder goes through a curing process to harden the coating. For powder coating, this involves heating the cylinder in an oven. For liquid paints, it might involve air drying or forced curing. Finally, the cylinder is marked with relevant information, such as manufacturer details, serial number, test pressure, and safety warnings. This can be done using printing, stamping, or labeling machines. The machines used in Repco N's production lines are sophisticated computer-controlled systems. Presses machines such as blanking, deep drawing, trimming use hydraulic or mechanical power to apply force through dies and punches, shaping and cutting the steel. They are controlled by PLCs that manage the ram movement, force, and speed. Flow-forming machines use precise hydraulic systems to control the movement and force of the rollers that shape the rotating cylinder preform. CNC systems govern the entire process, ensuring accurate wall thickness and dimensional control. Automated welding systems, SAW, GMAW/MIG, use robotic arms or specialized fixtures to position the welding torch and control the welding parameters. CNC controls ensure consistent weld quality and penetration. Heat treatment furnaces use precise temperature controllers and controlled atmospheres to achieve the desired heat treatment cycle. Hydrostatic testing systems use pumps, valves, and pressure sensors to control the pressurization and depressurization of the cylinder. Data acquisition systems record the pressure and any changes in volume, ensuring compliance with safety standards. Shot blasting machines use compressed air or turbines to propel abrasive particles onto the cylinder surface. Dust collection systems capture the spent abrasive and dust. Coating booths provide a controlled environment for coating application. Electrostatic spray guns charge the powder particles, ensuring they adhere evenly to the grounded cylinder. Metal spinning machines are made of a headstock, tailstock, and tool rest, all mounted on a sturdy bed. They operate by clamping a metal disc against a spinning die using a follower block. Repco N provides a comprehensive, integrated solution for LPG cylinder manufacturing. Their turnkey approach, combined with their expertise in metal forming technologies and automation, allows for the efficient and safe production of high-quality LPG cylinders, meeting international standards. They provide all the necessary equipment, software, and expertise to establish a complete production facility. HAEUSLER's VRM 4-roll plate bending machine is a modern device, specialized in bending thick metal plates with high precision. The machine's components include a sturdy frame made of high-strength steel to ensure stability and long life. The 4-roll system, with a flexible upper shaft and 3 lower shafts supporting the shaping of the steel plate, is the main component in shaping. These shafts are made of super durable steel, with good wear resistance. In addition, the machine is also equipped with a powerful hydraulic system, which helps provide precise pressure to the shafts, ensuring stable bending performance. The operator can easily set parameters such as radius, bending angle, and plate length. The system also has the ability to store old bending programs, saving time and increasing production efficiency. Along with that are sensors that monitor position and pressure, ensuring the bending process is accurate and safe. The machine's workflow begins with the preparation of a sheet metal that meets the standard dimensions and flatness. The sheet is then placed between the rollers, and the sensor system automatically aligns it to ensure accurate positioning. As the machine operates, the upper roller applies pressure to the sheet metal, while the lower rollers adjust to create the desired bending shape. This process can be repeated over several steps to achieve the desired curvature. TEBIS AG is a global leader in CAD CAM and MES software solutions, specializing in optimizing manufacturing processes, particularly for complex parts found in die, mold, and model making, as well as general machining. Their software doesn't build the machines, but rather provides the crucial intelligence, the highly sophisticated CAD CAM software and the MES software that drives CNC computer numerical control machines, automating and streamlining the manufacturing workflow. Their focus is on reducing machining time, minimizing material waste, and improving overall production efficiency. The creation of a 1.5 kilograms magician's hat from a 37 kilogram aluminum block is a prime example of subtractive manufacturing. This means starting with a solid block and precisely removing material until the desired shape is achieved. The process is a multi-stage operation, with TEBIS software playing a pivotal role in several key areas. The process begins with a detailed 3D CAD model of the magician's hat. While often created in separate CAD software, TEBIS can import and work seamlessly with various CAD formats. Within the TEBIS environment, the model is prepared for machining. This includes defining the raw material, the aluminum block, specifying tolerances, and incorporating features for secure clamping during the machining process. CAM programming is where TEBIS's CAM software truly excels. It takes the prepared CAD model and generates the toolpaths, the exact instructions for the CNC machine's cutting tools. TEBIS's advanced algorithms consider numerous factors, selecting the optimal cutting tools, end mills, ball nose mills, etc., for each stage, roughing and finishing. Implementing efficient roughing strategies like high-performance cutting (HPC) or high-speed cutting (HSC) to remove bulk material rapidly, devising finishing strategies for a smooth, precise final surface, ensuring collision avoidance through comprehensive simulation, and continuously optimizing toolpaths to minimize machining time and tool wear. After toolpath generation and simulation, TEBIS's post-processor converts the data into G-code, the specific programming language understood by the chosen CNC machine. This ensures the code is perfectly tailored to the machine's control system. The G-code is then loaded into the CNC machine, typically a multi-axis, likely 5-axis, milling machine, capable of complex movements. The aluminum block is securely fixed, and the machine executes the G-code, precisely guiding the cutting tools to remove material according to TEBIS's optimized plan. The CNC machines are the 5-axis milling machines. Its operation depends on the spindle that holds and rotates the cutting tools. The machine axes guide the tool and the workpiece according to the G-code instructions. The tools and workpiece are cooled during the process, and a feedback system is used to monitor the work for accuracy. Inspection and final touches. Once machining is complete, the hat undergoes rigorous inspection, often using coordinate measuring machines, CMMs, to verify it meets the required dimensions and tolerances. Any final steps, like deburring, removing sharp edges, or polishing, are then performed, either manually or through additional automated processes. The core of the physical machining process is the CNC milling machine. It's a robust machine with a worktable for the workpiece, a spindle that holds and rotates the cutting tool, and multiple axes of motion. The CNC control system interprets the G-code and directs the machine's movements. A 5-axis machine, crucial for complex shapes like the hat, allows the tool to approach the workpiece from virtually any angle. The spindle rotates the cutting tools at high speeds, while a coolant system manages heat and lubricates the cutting process. The MES software is used for production planning and control. In conclusion, TEBIS provides the sophisticated software that intelligently plans and optimizes the entire machining process. The CNC machine, guided by TEBIS's output, executes these plans with exceptional precision. This synergy between software and hardware allows for the efficient and accurate creation of intricate parts like the magician's hat, demonstrating the power of modern manufacturing technology to transform raw material into a finished product with minimal waste and maximum efficiency.